Good morning and thanks for joining. So my name is Jose Maria Garcia. I'm from Sevilla, from the University of Sevilla, and also involved in LifeWatch Spain, JRU. And today we're going to talk, me and AJ, about semantics and basically some of the basic concepts around the importance of semantics and also other issues about accessing data and so on and so forth. So you go on, please. So basically, the outline today would be first to introduce semantics in a very easy way, so that if you haven't had any contact whatsoever with semantic technologies, I will try to give you a good introduction about the basic concepts of how to develop semantic information, how to create ontologies, and so on and so forth. Also, all the basic tools that we have. Then we'll talk a little bit more in detail about linked data and why this is very important nowadays for the next part to make your data fair. Okay, I'll try to also sum up the fairness requirements or principles and how semantic technologies help there. We'll see a specific example on how can we apply semantics to the research data lifecycle. So focusing on curation, how can we introduce or improve the information and the data quality by using semantics. And then finally, AJ will also talk about security issues when accessing data services and some specific elements of security that you have to take into account for that. At the end, during the breakout session, we'll also try to have a hands-on session, but unfortunately, since I cannot share my screen, it will be quite well. We'll see how it goes, but yeah, we'll see. So please go on, AJ. Okay. So first thing first, what's the meaning of semantics? What do we mean when we talk about semantics in general? Well, we can define semantics in several ways. First of all, it's the study of meaning, reference or truth, as it says in Wikipedia, right? So basically, we are talking here on giving some meaning to the information that we handle, that we manage in our day-to-day business. So another definition could be this one from Oxford that you can see there. That's basically semantics is a branch of linguistics and logic, okay, which is concerned with meaning. So basically, the key concept here is that with semantics we can also reason about the information that we have. So we can basically get more information from this, more value from the information that we got if we apply some semantics to there. Okay. Going closer to what one can think about semantics when referring to computational aspects, okay, of semantics, is that by the use of semantics we provide some basically a way to the computer to interpret the data which is in basic, which is apart from just in a syntactic way, okay? And then basically we constrained the interpretation, or we drive how can we interpret data by using this information, this semantic information, okay? So next slide, please. Okay, so this is what semantics is, and today we are going to talk about semantic technology, which is basically a way to use formal semantics into computational services, and basically by using semantics, we are able to add this formal layer to the data. Okay, and specifically when we talk about data on the web with semantic technology, we can basically use some specific languages and formal languages to express and to define the relationships between different elements of the data, and also the meaning, the internal, the logical meaning of that data, so that machines can process the data in automatic or semi-automatic manner. Okay, so that's the key aspect here, and this is our goal when using semantic technologies. Okay. So next slide, please. Okay, so to give a little bit of context on where this comes from, basically, the web, as we know, as we used to know it, was basically considered or designed as a web of documents. Okay, so basically we had their elements that are documents themselves, and basically each of these elements are described using some standards like HTML, XML, and we have some ways to refer to them using URIs. And the basic interactions between the web of documents, the so-called web of documents, was using HTTP protocols, so standard protocols again, and we can somehow traverse the web of documents using hyperlinks, okay, between these documents. The problem with this old-fashioned conception of the web is that, first of all, the links that we have between the different documents are untyped. So that means that we actually don't know where we are going. Okay, we have to basically consider all the context, and usually for machines it's nearly impossible to learn. Well, you can apply always some natural language processing methods, but it's quite difficult to know where we are going by traversing these links. Okay, so the relationships between the different documents are not clear. And then if we want to search for complex, we want to use complex queries in classical search engines, they basically fail because they don't have the information about what we are looking for. We just make syntactic queries. Okay, we don't. The search engine doesn't know actually what we are looking for. It just tries to match the terms that we use in the queries. Okay. So in the next slide, basically, we're showing that we basically are moving, and I think that we are already quite there towards a web of data, where instead of having documents and hyperlinks between those documents, we have things, we have entities on the web, and that we can access them, and we can traverse and navigate through this web of data by using type links. Okay, so that's the evolution of the web, or the future internet, where we are going, or where we are mostly there. Next slide, please. So what are the characteristics of this so-called web of data? Basically, we have links now which link arbitrary things. Okay, so it allows us to link entities such as a person with locations where this person has birth, with events, and we have many different entities, all of them related through links, which are typed. Okay, so now we explicitly say that when we are navigating through a link between different things, we know where we are going. We know the meaning of that relationship between those entities. Okay. Still, the things that we have described. So instead of having web pages, we have things inside those web pages, inside those documents described, and we can even identify them by using URIs directly. Okay, so we have a more complex and more rich information about what we are using throughout the web. Okay, you go to the next slide, please. So this basically is what the Semantic Web tried. Okay, so the Semantic Web was or is the vision from the W3C of how to get to this web of data. Okay, so the evolution of the classical web of documents into a web of data. So the main goal, the main objective is to make the web machine readable. If we have these things identified on the web, and the links are explicitly typed, then it's supposed that we will be able to process in an automatic or semi-automatic manner, as I said, the web, the information that we have there. So some benefits that this can have for us is that we will be able to automate some of the tasks that we usually do manually on data. Okay. It also enables knowledge sharing and reuse, which is quite important, which is basically the cornerstone of the FAIR principles, as you know. And we can also have a separation between data and the way that we represent the data, and the tools that we use to manage or to modify or to analyze this data. Okay. So basically, the semantic web is can also be defined as a set of standards that can be used to provide well, this vision of the web of data. But the problem is that this original vision that Tim Berners-Lee had when he created, when he devised this semantic web, did not succeed. Okay. Basically, this is this has something to do with those standards that were defined at the beginning, which are quite heavyweight, difficult to understand and complex to define, and all that will basically also derive in a little uptake from the industry of these standards. Okay, this is something like similar that it happened, if some of you know, with SOAP services and WSDL and this WS asterisk standards that they didn't actually they have been used, but they didn't actually went to the public, let's say, to a widespread use of them. So next slide, please. So anyway, within the semantic technologies, we usually use also this stack here, this diagram that you can see here, that basically shows you the technology stack on how the different layers that we use when describing semantic information on the web. Okay, using semantic web technologies. So you can see on the left-hand side of this cube, you can see basically the main concepts that are used. So at the bottom, we have the web platform. So standard standards from the web, from the original web, are used as the basis, as the foundations for the rest of the elements that provides us this way to add semantics to our data. Then we have the syntax layer on top, which basically provides us several ways to serialize information, semantic information, and a way to annotate those previous documents that we have on the web. The knowledge representation structure is, as we will see right now, is based on Rdf, and then on top of that we have the upper layers, which are about reasoning, inferencing, logic, and then the applications that make use of those elements. Of course, trust, security, proof are also quite important, and we will also consider security aspect, as I said at the end of this session. So let me focus on the basic parts of this semantic technology stack. So we'll now learn how knowledge is represented, okay? And then we'll talk about adding semantic information to this data model, let's say. So next slide, please. So the first, let's say, the first three layers that we have in this figure basically allows us to represent the information, okay, in a certain way. And in Semantic Web, we usually use the resource data framework for defining the model, the most basic data structure that is used on the Semantic Web, okay? So Rdf, or the Resource Data Framework, or Rdf, is basically based on triples. So we have different entities which represent, basically these entities represent some real-world elements, some real-world entity, and each of these entities are identified. So they usually are identified by using IRIs, which is in internalized resource indicators. Identifiers, sorry, which is close to what a URI is, if you can think about it. And basically, what we have here is what you see at the bottom left. It's this is the basic element of Rdf, a triple, where you have three elements related. So we have a subject, and we have a connection with another resource. So those are called resources, and this connection is made by a predicate. Okay, so we have a subject, the predicate, and then the object. Okay, and basically both the subject and the object can be entities, but also objects can be literal values. Okay, and we also make use of some namespaces. In the next slide, we have an example of this. So here you can see an example at the top of representing some information in a semantic way using Rdf. Okay, so the bubbles that you see there are entities. So those are resources that we can we want to add information on top of them, about them. So you see there this FOAF, this is basically a namespace which represents a specific vocabulary, a specific semantic vocabulary, which is friend of a friend, to basically define, it allows us to define, to describe persons and their relationships, and some other things. And then you can see here that we have two entities. So we have Ian and Mary. Okay, those are basically represented there as this FOAF Ian and FOAF Mary will be the identifiers of those entities. Okay, and this will basically be an IRI, as I said before. So you can think about a regular URI with some common path, which is the fourth part. Okay. And then they are related via this association called flow of nodes. So here we are saying that the entity represented by the identifier flow of ion basically knows some other entity, which is Mary. So in this case, and you can see on the right hand side, you can see an example of a predicate pointing to a literal, a value, okay, an actual value, such as in this case the first name of this entity is Mary. Okay. So of course this is a graphical representation of what RDF is, of an RDF model, and RDF can be serialized in different formats. Okay. Usually or originally it was devised. The main serialization would be an XML serialization, but nowadays there are also other more understandable for humans and more manageable, such as Turtle or JSON LD. So there in the box you can see the equivalent in Turtle language of the graph that you see at the top. Okay. So basically, you see here again this structure of triples. This structure of you have first the subject, Ian, the predicate, knows, and the object, Mary. And the second one also a different triple, but in this case with the object being a literal. Okay. Can you go to the next slide, please? Okay, so with RDF, what we have is just the model. We still don't have semantics there. We only have a way to represent information, which is based on these triples, but we actually need to add some additional information on this model to actually provide semantics to our data. Okay, and this is where the next layer on this semantic technology stack. It's also called the semantic technology cake, and basically in this layer we have we have three main facilities or three main standards and specifications that allows us to include this semantic information on top of the data model. Okay, so the first one is RDF Schema, or RDFS in short. It's basically it provides a very easy and lightweight way to create vocabularies and to create models on top of RDF data. Okay. Then we also have SCOS, which is a simple knowledge organization system, and it's basically provides us facilities to represent taxonomies, glossaries, thesauri, and so on. So basically to have these classifications of data, which provides, of course, this reasoning and inferencing functionality here. And then finally, we also have the web ontology language, or OWL, which allows us to specify RDF ontologies, which are on the semantic web the most complex way to describe semantic information and to add semantics to data. Okay, so let's go a little bit deeper on each of these elements, so you know basically the basic constructs that they have. So next slide, please. Okay, so RDF schema, you have there the link. Basically with RDF schema we can define the terms that can be used in an RDF graph. So that means that we will basically model the vocabulary, the different properties, and the different types of the entities that we can have. Okay, so we are now again adding this information about types, about how the things are related, okay? And basically with RDFS we can have classes which you can consider them also as or interpret them as a conceptualization, okay? So it's we can have properties, we can define properties between different entities, okay? And we can restrict those classes and those properties to have certain to cover certain constraints of our scenario of the data, on how the data can be defined or should be defined by using this vocabulary. Okay. So the main construct then when using RDF schema are classes. Okay. And in RDF, everything is considered a resource. So we have an RDFS resource class, okay? And basically the resources can be instances or individuals. They are also called individuals of some class. So we can say basically that some entity with we have an entity identified as we saw before, with a URI or a IRI. And then we can say that this particular entity belongs to some specific class by using the RDF type property. Okay, so we will have triples in our model saying that some specific entities are of or belong to a certain class. So basically, they are a representation of certain concept. Okay, by using RDF type. This allows us to have actually hierarchies of different classes, so we can have relationships between different classes. Since each class is an RDF resource, we can also have information about the class of those classes or subclasses and so on and so forth. And one key concept here also is that you can have resources. Again, resources everything in RDF, but you can also think about entities if you prefer that analogy. They can belong, or they may belong to different classes at once. So we can have something that is both a person and that is both a female person. For instance, if we have a person class and a female class in our vocabulary. Okay, usually there will be these two classes. This example will be an example of subclassing between them, but you get the idea. If you go to the next slide. So then properties can also be constrained. So basically in RDF schema, we have ways to say which should be which domain should have a specific property, and also the range, so that we can constrain the classes that can be used as a subject of a triple of a certain property. Okay, when we talk about property, we basically are talking about the predicates in the subject predicate object form, okay, of a triple. And again, as with classes, we can have sub-properties here. So we can basically inherit or let's say we can further constrained properties in a hierarchy. Okay, so that properties higher in the hierarchy may use a more generic domain, for instance, or range for the object, and then sub-properties lower in the hierarchy could constrain more the types, the classes that can be used in those properties. So you remember that predicates can have literals also as values. So in RDF schema, that we can also constrain which the data types that we can have in properties, in value properties, value-based properties. For that, we can use XML schema data types, for instance, and we can also add some internationalization information to the strings that are there. Finally, we also have with Rdf Schema the also other facilities to annotate the models that we create with Rdf Schema, and basically we use the two properties, RDFS label and comment, to provide information in a human readable way to the resources that we use in our scheme. Okay, we'll probably have a look at some examples in the hands-on session afterwards. You can go to the next, please. Okay, so thanks to these modeling facilities, we have with Rdf Schema, we have the possibility to inference, to obtain, to reason about those elements. And in the case of RDFS, this is a basic reasoning facilities, which basically are summarizing the entailment rules that we have. Basically, with the entailment rules, we can extend the RDF graph, making explicit the relationships that we created before. So, for instance, if you have a subclass relationship between a certain class A, which is a subclass of B, and you say that some entity called also A and lowercase is of type A uppercase, okay? So it's basically the class of this A is A. Then with entailment rules, we can infer, we can get additional information, such as that A is actually also of type B. Okay, so it also belongs to the class of resources represented by B. Okay. So in the end, RDFS is very useful to define vocabularies in a lightweight manner. Okay, so we have those constructs that I've told you, and we can basically make these constraints about the relationships, the basic relationship that we have between classes, properties, and also even link with external classes, which we'll see that it's very important for the realization of the semantic web vision. Next, please. Okay, so very quickly about SCOS. As I said, basically with SCOS we have additional elements to represent taxonomies, thesauri, glossaries, and so on. And basically, what SCOS provides us is an additional vocabulary that we can use when defining a model using RDF and RDFS, which allows us to identify concepts in general. Okay, so before we were talking about classes, here we are talking about a concept in that let's say logic way. We can annotate those concepts with labels, with different labels, different ways to refer to those concepts with SCOS, and we can also provide information about hierarchy or how different concepts are related. Okay, in terms of the scope, for instance, we can say that something is a broader concept than other things, and we can also define collections. So basically, it allows us to provide more information on the model. Next, please. So the problem with RDFS and SCOS is that basically the inference, the reasoning that they provide is quite limited to only these subclasses, concepts, sub-properties, domains, range, and nothing more. And the constraints that we can have for properties are very simple. It's just we can just say which will be the domain and the range, and probably some relationship between different properties, but that's it. Okay, we cannot say more about them. And also SCOS doesn't support individuals, so we can create categories and classification schemes, but we cannot actually create individuals or instances of those classification schemes, let's say. So in the next slide, we talk about the most let's say complex way to add this information and to basically tackle these limitations that we said before, which is the ontology web language. So with OWL, basically we can describe ontologies, and an ontology can be defined as basically as a formal specification which is made explicit. Okay, so we have explicit definition or specification of some shared knowledge, some shared conceptualization. Okay, so it's a way to precisely describe a domain and in a way that it can be shared in a community. Okay, and we can use this specification to create or to describe data. Okay, so without ontologies we have more reasoning facilities than before, but something that you have to take into account is that all is based on the open world assumption. So that means that if we don't specify something and we use all, it doesn't imply that this doesn't exist. So the absence does not imply the negation of the constraint. Okay. Another problem that you may have when using this open world assumption is that there are no unique names. So actually, even though we have IREs or identifiers to refer to some entities, we cannot assure that two different identifiers can be referring actually to the same real concept, okay, to the same real entity. And for that, we have to use, well, entail mechanism and basically the same as property to tell the reasoner and the underlying system that these two entities are actually the same, even though they are referred as different, but only at the identification level, let's say. So this could lead to some problems. So we have to be careful when using all. Next slide, please. I'm not going to go much deeper into the details on the different facilities that OWL provides us to describe this semantic information, but basically for you to take into account that we have much more powerful mechanisms to create or to define ontologies with OWL, is that we can have algebraic properties on basically on those the original property that we have in RDFS. We can now say that that certain properties reflexive, or certain other is symmetric, and so on. We can say that properties are disjoints, that we cannot have same ranges. Basically, we can qualify the cardinality of those properties, and basically we can restrict the values, the classes that we can have as domains or as ranges of properties in a much more complex way. And that will be quite useful when trying to classify elements in different classes. Okay, so this is quite handy for us in this case. Well, we have many other facilities, just like unions and disjunctions, equivalence, and so on. But basically, this is a quick summary. So next slide, please. The problems that we have with OWL is basically that it's sometimes may be too complex for us. Okay, and actually, in the last standard definition of OWL, which is OWL2, they define different profiles which limit the reasoning capabilities to certain scenarios, maybe limiting the expressiveness of the elements that we can have in an ontology to provide better performance of the reasoning. Okay, but the main problem with our ontologies is that they are heavyweight by nature. Okay, so if we want to actually describe some vocabulary for describing a data, and for a certain scenario, we have to specify many different things using OWL, because if we forget to put something there, as we are in an open world assumption, we can reach conclusions that are not or that are not consistent with what we thought at the beginning. Okay, so sometimes it's possible, or it's enough to just use RDFs or even SCOs to describe ontologies, or in a more lightweight way, and we can basically we are fine with that. Okay, so those are usually called vocabularies instead of ontologies because they are much more restricted, but you get the idea. So because of this heavyweight definitions problem that the old ontologies have, this is one of the reasons that the original semantic web vision didn't uptake, took some the sufficient uptake in the real world. So if you go to the next slide, so we are now going to explain quickly what's the current situation, let's say, of a semantic web and how we reach.
Is it possible to ask something in between? Because before
sure. Yes,
so
sure. Sorry.
I'm not sure if you tackled the difference between OWL full and OWL light, or because you mentioned here OWL full.
Yeah.
So can you say something about it?
Yeah, I said that basically in when using OWL, you can also restrict yourself to just using some specific profiles. So profiles are the way in OWL2 how they basically restricted the facilities that you can use to define ontologies, so that you get into situations which are more performant in certain scenarios. I mean, there are three different profiles, okay, and depending on the type of data that you want to describe, you can pick one of those profiles.
Yeah, but there are problems with OWL full, right? You can specify a lot, but so I never really captured. So I never really worked with OWL full.
Yeah,
so
no, me too.
OWL DL also, right?
Yeah, no, yeah, that's true. I haven't said that. Yeah, basically the logic formalism behind OWL. Again, if you use you can basically pick and choose the elements that you want to use, and if you restrict yourself to OWL, which is description logics formalism, then reasoning is to a certain extent achievable in the sense that it can be performed in a good manner, let's say. But yeah, all full, I don't recommend that actually to use the full profile of OWL, because it's too complex, as I said, and usually it's not tractable by reasoning engines.
Thanks.
Okay, so you go to the next slide. Okay, so I want to introduce what linked data is by first introducing what is a knowledge graph. Okay, so basically knowledge graph is a knowledge base. Okay, it's you can consider it as a database. Okay, in some sense but it uses a graph structure data model. As you saw before in RDF, we have these nodes and these predicates between those nodes. Okay, so this is essentially the same idea, that we have a data model in a structure using a graph, so that we have several entities that can come from different sources, integrated and linked together using these predicates in this case. Okay, with knowledge graph, the thing is that in comparison to traditional databases, okay, we don't have a global schema. We have a set of schemas that are related somehow, okay, within the knowledge graph. And by using knowledge graph, as we are not tied to a specific schema, we can actually change the global, let's say, appearance of the knowledge graph, the structure, very easily, so that we can interlink new data and create new connections between different data using different schemas without affecting the rest of the graph. Okay, so here on the right hand side you have an example of a knowledge graph where you can see with the bubbles are basically the entities that are described in this graph, and then the relationships between those entities you can see there. So here we have Harrison Ford, which has a character in a movie, which is Star Wars, and Star Wars has Harrison Ford as an actor, and you can see that there are other movies there also. But we also have in the end information which is not about movies, but for instance about other professions, like this cyclist there, which is also integrated in the same graph, and we can basically traverse this by using different elements and different types of links. So the most let's say the most visual application of a knowledge graph is actually the Google knowledge graph. Okay, so how Google makes use of this information is in the next slide. You have an example. If you can, there you have it. So basically, what Google did with knowledge graphs some years ago, and they are still improving this, is to add to searches this semantic information. And this semantic information is basically the boxes that you see on when you use the search engine on the right hand side, and there you can traverse those links on the knowledge graph and follow the related entities with this search. In this case, okay, you can go to the different movies where Harrison Ford were participating, and so on and so forth. So basically, this is the main idea behind linked data, actually, which we have a huge graph, okay, of interconnected entities that we can traverse. So if you remember from the beginning, this is basically the web of data that we are trying to reach. So next slide, please. Okay, so to define a little bit more linked data, we can consider that basically linked data is the use of semantic web technologies within the web to publish structured data and to define those links. So basically the realization of the web of data. Again, we use URIs as name for things to identify them. So in this case, one key concept of linked data is that we can look up those URIs and to find more information about those entities. Okay, and then we can keep on discovering new things by traversing the different links between these URI. Okay, next slide, please. Okay, so in order to come up with link data, well, this is the so-called 5-star link open data is basically the requirements that you have to meet in order to consider that you have link open data in this case, okay, published on the web. So these 5 stars are basically the different levels that we should try to reach to actually cover all the basic definition of what link open data is. And you can basically consider this as a first version of the FAIR principles, okay, somehow. So the first star is you have a 1-star data if you provide this data available on the web using whatever format, but in an open, using an open license, so it can be accessible there. Maybe you can go to the next slide where we have more. Yeah, so the idea here is that data can be accessed easily, and we can even download the data and store it locally, and we can import this data on other systems, on different systems. Okay, so the next slide will describe the second level, which is available as a structured data. Okay, so here if we provide some structure of our data, basically we are starting to add information about the semantics that are behind them, using, for instance, Rdf, but it's not necessary at this moment. So basically, we can allow the data to be processed, okay, by different software. And as we use structured data, we could also export or transform this data into different formats. So this is second level. The next slide will be to go into a non-proprietary format. So in that way, if we use structured data but using a standard, then we can basically use this data in whatever system that we may have, and we are not tied to a particular system, proprietary system. The next level, the fourth star, will be to use open standards to identify things. So now we are starting to use URIs to identify elements. We are starting to use Rdf to describe the information there, and we will link together the different elements of our data within the same, let's say, the same data set. And the last part, which is the next slide, is to link our data to outside data, basically adding value to our data by interlinking different data sets between them. And this will allow us to discover new data, as we said before. And of course, this is not easy because we have to find out which are the data set that can be linked to our data set. We have to find out which vocabularies can we merge into our data and interlink together. But this will basically provide a full link open data structure to our data. So next slide, yes. So there is something that, well, basically this link data has been evolving throughout the years, and there is an initiative called the Link Open Data Cloud. You can go to that URL, as you can see at the right bottom corner, where basically they were collecting information about the open data sets, the link open data data sets that are available. Okay, so it started in 2007, and you can see there different data sets that are related with each other, okay, that are linked. And if you go to the next slide, you will see the evolution. Okay, so well, in this case, of course, the link open data cloud is basically an interconnected set of these data sets, okay, and these are published following the link data principles. And at this stage, we basically have a big data set, which is DBpedia. Okay, this was basically an RDF-based version of Wikipedia. Okay, and some music-related data sets also there, and basically that's it. And by that time, we have 1 billion triples there of data and 250K links. Okay, but this, of course, evolved. Next slide. So here it's a snapshot of 2009. You can see that there are many more data sets. So next slide. So in this case, at this stage in the link open data cloud, there were 295 data sets, and now we have 31 billion triples and more than 500 billion links between different data sources. So you see that this cloud is where we're forming a real intricate a graph, a knowledge graph, or a worldwide, let's say, knowledge graph of data sets. Okay, so this, of course, evolved. If you go to the next slide, and we reach nowadays, basically this is the last diagram that they had in November last year. You can barely see anything here in this case, because at this moment in this initiative they have registered 1,000 more than 1,200 data sets. Okay, and well, in this case they are basically clustering the link open data cloud in 9 subdomains, and they have government, they have they have well, if you go to the next slide, they even have a subdomain about life sciences. Okay, and you can see that it's actually the biggest subcloud, the biggest subdomain in the link open data cloud. This is especially because of the contribution from Bioportal, which you may already know, and they basically have their many different data sets related. You can see that even the relationships in the graph cannot be seen at this zoom level on the picture, but each of these bubbles are those data sets, and the brown ones comes from Bioportal. They are also from Rdf, and in purple, and some others there. So this is an ongoing effort, of course, and this is pretty good to get the idea of the importance that the link data has got throughout these years, and that I think that this is basically the actual realization of the original semantic web vision in a much more lightweight way. Okay. And of course, there are in the environmental science, there are also similar approaches to have a registry of the different ontologies and data sets and vocabularies that are used in this branch of science, like for instance the Eco portal in LifeWatch. Go to the next slide, please. Okay, so let's talk a little bit about fairness and how semantic technologies provide us a way to achieve this machine actionable fairness in our data set. Okay, so next. So you know basically the FAIR principles, and here I just want to stress the importance of semantics and how they play a fundamental role in achieving the fairness of your data. So it's very important that you know all the pieces that have to be used together. So yeah, the main idea with FAIR is that we will allow, by having FAIR data, our systems, our computational system, to find, access, interoperate, and reuse the data in an automatic fashion, or as automatic as possible. Okay, so if you go to the next slide, when we talk about having data to be findable, so the basic principles of FAIR says that we should have unique and persistent identifiers assigned to data and to metadata. And this is covered in semantics with semantic technologies by using URIs and PIDs, basically. They say that the data has to be described with rich metadata, and by using linked data vocabularies, we can achieve this. Then the metadata should clearly include the identifier of the data they describe. Basically, we have to make explicit the link between the metadata and the data, and this is basically the fundamental facility that we have with linked data, and using Rdf, for instance, for that. And finally, to have findable data, we have to register this in a searchable resource. So for that, we have already many implementations that provide efficient ways to query and to search for elements for data by using semantic technologies and Rdf, all vocabularies, such as the triple stores that are available. Next one, please. Okay. So to be accessible, we have again 4 principles that we have to follow. First one is that the data that we have and we want to publish should be retrievable by using their identifier and using standard communications protocol. So again, this is covered by using URIs for identifying our elements as linked data proposed. The protocols that we have to use should be open, free, allows for authentication and authorizations where necessary, where this will be covered by AJ afterwards at the end of the session. The last part. And then finally, metadata has to be accessible even when the data are no longer available. And this is achievable by using semantic technologies and by using knowledge graphs, since we have, as we said, we have independent graphs related together. Okay, so we can have a definition of the metadata, which is linked with the actual data, and if we lose the actual data, we still can have the metadata there. Okay, because they are not, let's say, stored in the same global schema, so they are independent. The next slide, please. So about interoperability, this is basically the main goal of linked data. So we can use formal language for knowledge representation, RDF, RDFS, OW, different serialization formats such as JSON LD, for instance. We have to use metadata and data that we have to use vocabularies for data and metadata that actually follow FAIR principles. And as I said, linked data vocabularies, they are fundamentally following these same principles, as I said before. And then again, the data should include qualified references or typed references to other metadata, so we know their relationships between them. Okay, so this is also true by using semantic technologies. Next one, please. Okay, so finally, for reusability of our data, again, we have to try to describe as many attributes as possible about our data and about our metadata, and this can be achieved by using different several metadata vocabularies, for instance, which can be interlinked together, as we saw before. The data has to be released with a clear and accessible user license, where this can also be actually annotated, this data, by using license ontologies. So Creative Commons, for instance, has an Rdf model available that we can use directly there. Provenance information is also very important, where there are many different provenance vocabularies available. And finally, they have to have a reusable data. The data has to meet or has to follow domain specific standards, and for that we can rely on domain specific ontologies and vocabularies that are being developed in different communities, like in ENVRI, for instance. Next slide, please. Okay, so now I'm going to describe or to provide more insights into how to apply semantics within the research data lifecycle, with a specific example of a specific activity in this lifecycle. So if you go to the next slide, you probably know this research data lifecycle from ENVRI reference model, which is basically the cycle of these 5 activities, where we have acquisition of data, then curation, publishing the data, making it accessible, processing and analyzing the data, and using the results there, and potentially starting again the cycle. And here, semantics can be very useful for each of these 5 activities or processes. So first of all, for acquisition, we can, right from the beginning, include metadata when we are acquiring the data. For instance, we can even use, we are using sensors to acquire information. There are sensor vocabularies that can describe the data that is generated by those sensors, the observations that we have. So we can, right from the beginning, use semantic to provide an added value to this process. On the curation part, we can basically use Rdf stores to store the metadata that is originated, and including here some key issues like versioning, identification, and citation, and so on. And when publishing, of course, by using semantic technologies, we can pretty much ease the way we can search and query those systems, and we can discover new resources related to them. About processing, we can also use semantic vocabularies to describe the processes themselves. So we can have workflows, for instance, described by using specific semantic vocabularies, and we can have engines that make use of these the semantic definitions to actually execute those processes. Okay, and then finally, for using the data, we can in the end have even data services that provide us the way to make use of this data that has come through all the whole cycle, and we can basically, on those data services, we can describe them using, again, metadata, semantic annotations that provides us information about how these services work. You go to the next slide. We are now focusing on curation, okay? And let's see the importance of semantics in this specific process, okay? So, well, curation, if you go to the next slide, is basically the main goal of data curation. The next slide, please. is to add value to the data that we have already acquired. Okay, so there are many different definitions about what data curation is, but basically this all revolves again around the same principle of making the data useful for the users, being them academics, the industry, or the public, the public world. Yeah. So and we will, by adding this value and adding information to the data, that will ease the discovery and the use, the later use of the data itself. You go to the next slide. So why the data curation is so important? So basically, if we think about how we collect all the data that we use every day, we can have data from different sources, raw data. Let's say we can acquire data, and we in our daily business we use many different sources of data. This basically can form what is called a data lake, which is basically some sort of repository where there are vast amounts of raw data. Okay, and each of these data has its own format. Some of the data will be unstructured, some will be structured. Some of the data will be obtained by calling external systems and other computational systems, and basically we have all the data there in a unstructured collection. Okay, the problem with data lakes is that if you go to the next slide, is that they may become data swamps. Okay, where basically we lose the organization of the data. Then, and if we don't have any curation at all there, it will be a nightmare to actually perform data governance or activities there. Okay, and in the end, it will render all data unusable. Okay, and frustrating to use. So you go to the next slide. This basically sums up these ideas, and then this is why we actually need curation, right? So if you go to the next slide, you can see basically the one example of a data curation lifecycle from the Digital Curation Center, which basically revolves many different activities, and in most of those activities, semantic information is crucial. Okay, and we need to include that information there. So next slide. Yeah, basically the generic activities that you can see at the center of this diagram, which is the way we describe and represent information. There we can basically use semantics, use RDFs and SCOS standards, for instance, to create to describe the data, and we can use vocabularies to assign metadata to this data. So this is a crucial part of data curation. This is the way we represent and describe the information. Yeah, there are other activities like preservation, planning, community watch, curate, and preserve, but basically this is the most important for us. The next one, please. So in the sequential activities, when you basically start by conceptualizing, the data, basically that comes from data acquisition, you create or receive these data sets, and there you assign the metadata directly in that step, right? So we use semantic vocabularies to that. For a price and sell it, basically this part of this task is about evaluating the data, having into account quality aspects and adherence to different policies. We can use here again different vocabularies for helping us on that. Then we go into the ingest activity, which is basically to transfer data to some archive, such as a repository, and there we can have a semantic repository for that. Next slide, please. Then we have a preservation action, which is about having ensuring the long-term accessibility of the data, and access, use, and reuse as in FAIR. Okay, so here again we have importance of the semantics technologies, and yeah, and then occasionally we will transform it into new data and maybe migrate it or something like that. So if you go to the next slide, I just sum up here the need for semantics in data creation, and the real importance of this is that we have to, first of all, curation is about adding metadata, and for that we can certainly, and we should certainly use semantic vocabularies because they allows us to annotate seamlessly our data and data sets and provide this needed context. That will be useful also for accessing, for discoverability, and for other tasks that you will see during the winter school, during the other sessions. And basically this provide the building blocks to reach the fairness of the data for the whole research data lifecycle, as we said, we've seen before. So talking about metadata, if you go to the next slide. There are many different things that we can say by collecting or by curating some metadata about our data. Okay, so these are basically the 5 W's and plus 1 H questions that can be answered by metadata, right? So the who created the data, who maintains it, who uses it, and so on. When the data was collected, where was it collected. We can have information about the actual meaning of the data, the content, and the structure by using vocabularies, and the reasoning behind why the data or data set was created, and how was the process to obtain it, or how can it be analyzed. Next slide, please. So the metadata principles that we have to take into account is basically that metadata is different from data in the mode of use, but actually metadata is data in the end, and it's only the way we use metadata for our own purposes. And for some communities, what we consider is metadata, it could be data for them. Okay, so it will depend actually on the actual use case scenario. Of course, with metadata, we can annotate not only our data, but also the users, the services that make use of this data, the different computing resources that are needed to obtain it or to analyze the data, and so on and so forth. And also, very important is that with metadata, we allow actually to provide these links between different data sets, for instance, and also to give more specific context that will help us in processing the data. Of course, metadata must be machine and human understandable, and that means that we have to use, as we learned before, semantics. And also we can also have management metadata related with our data, not only a description of the data, but also the context, the management context, let's say, like which are the projects where this data has been being used or collected, and which are the funding schemes that that allowed us to get this data, and so on and so forth. So a little bit about some of these concepts about getting the metadata in a proper way. In the next slide. Very quickly, we talk about persistent identifiers. I'm not going into details on this, but basically it's fundamental for data creation to have the entities, the data, and the metadata identified uniquely. So we have to use mechanisms to obtain persistent identifiers that will be reusable and will be accessible in the long term. Okay, so there are many different options there, like using DOIs or minting URIs, specific URIs, and so on. Next slide. Then about some vocabularies, some semantic vocabularies that you can use to answer those questions about metadata. Well, the most generic ones that we can actually apply to our systems are Dublin core or friend of a friend, for instance, which is from the example that we saw before. So next slide. Provenance information is also quite important. There are vocabularies specifically aimed at defining the provenance information, which is very important in data curation activities. Okay, such as the Pro framework. You see here a hint on the different elements that the Pro framework has. Next slide. Then the data sets can be described using vocabularies themselves. Okay, so there is this vocabulary of interlinked data sets, void, which is actually the one that is used in the Link Open Data Cloud that I've shown you before. If you go there, you can find this information. And basically, it allows us to provide metadata about the dataset itself, like the license, the access points, the way they are structured, for instance, providing examples or providing the specific schemas or vocabularies that are used in the data. Next slide, please. Then data catalogs can also be described using semantic vocabulary. So the most used one is the DCAT, is data catalog vocabulary. It's a standard from W3C again, and it is the way we can interoperate between different data catalogs. Okay, if we have them described using this metadata vocabulary. Next slide, please. We also talk about quality assurance, and there are vocabularies for that, such as the data quality vocabulary that can be applied to the data set to provide information about the quality of this data. The next slide, you can see open citations if you want to basically relate or interrelate some data with an article that uses this data. There are vocabularies that allows us to actually make those links, like open citations that you can see here. Next one. And then finally, metadata that is domain specific, such as for the environmental science and research infrastructure, for instance, there are many vocabularies that can be used there, such as Darwin Core or EML, EMF. And next slide. For research infrastructures, you have the SORIF or even the ENVRI reference model vocabulary that you can, or ontology that you can also apply. Okay. The next slide will be finally. We will actually need some tooling support for doing this and for providing these annotations, these semantic annotations of the data for basically devising all the metadata information that we need. And there are several tools there to use, such to annotate them. There are tools or services that generates persistent identifiers for objects. Okay. And then there is some we also need some interlinking support, and there are also tools to customize the schema and to integrate different vocabularies and so on and so forth. So basically, this is just to say that it's quite important to have a tooling support. And well, this is all from my side. I don't know if I went too fast, but if you have any questions, you can make it now or maybe afterwards. I don't know if we have time. Yeah.
I have some questions. Yes. With regards to the, for example, I must say that I'm not. I usually don't work with data, and I'm more into the the data management plan perspective interested. Okay, so you mentioned the open citations, which is a way to interlink the data with, for example, papers that are cited, right?
Yeah.
Okay. So this is kind of, can you explain more how it works? Because I kind of lose track on the last slides that were very fast.
Yeah, I mean, I didn't want to go into much details there. Just mention some vocabularies that you may need, such as this one, and basically with open citations, you can basically describe or link together data sets. So if you have information about a data set, okay, you can basically link it with an article which is using this data set, for instance. And open citations is basically a vocabulary of different classes and predicates, as I said, in the RDFS part, okay, so that you can make explicit those links in the data itself, in the metadata itself.
Okay, that's what I wanted to understand. Thank you.
Welcome. Anything else? If not, I'll give the floor to AJ.
Jose Maria, can you hear me?
Yes.
Could you explain me, please, the difference between the URI and the PID? Because for me, it's not so clear, the difference.
Yeah. Basically, PID and a URI could be a PID, okay. But the key concept here with PIDs, with persistent identifiers, is that they basically, by having a PID, you are reassuring that the reference, the identifier, will be available in the long term. That's the key idea, okay? So you can have URIs that are such as a DOI, okay? It's in the end, it can be a URI that is minted, and if to consider this a persistent identifier, someone has to basically assure you that this will be accessible in the long term. So of course, with DOI, you know that you have we have this DOI foundation that basically assures you that to some extent. Of course, well, this comes more from the preservation part of the story, but you have to basically have a certain assurance on that, okay? And for that, with persistent identifiers, you usually rely on external entities, governmental entities or foundations, something like that, that binds those persistent identifiers for you, and then you use that, okay? In terms of how you use these identifiers in your data, on your metadata, it doesn't make a difference with a normal, regular URI, okay? But the key concept here is more it's more about the higher abstraction in this case, like having this long-term accessibility to the URIs, okay? Don't know if that answers your question.
Yes, but for example, in my organization, the metadata catalog is under an HTTP, no HTTPS. Then, for example, all the URIs cannot be considered PIDs. I'm right?
No.
For example, no. Okay.
they cannot be considered PIDs because no one knows if your organization may finish their operation. Let's hope it doesn't, but then it cannot be considered a PID in that sense. Okay. So if you make
let me can I say it's very
sure.
easy. And any URL, you know, can guarantee that URL is fixed forever. So the URLs are not valid PIDs because you need to move machine, you need to move direction. So you need other way to identify those objects. Whatever resource, you need a specific way to identify each of those resources. And those resources, you can use different way of persistent identification. There are different standards. There are different organizations that provide those identifications. And they guarantee that that identification is fixed in time forever. For example, I can have some specific services, so you can access some specific data sets using a URL, okay, but those elements are also registered, for example, in a handle database, and so you can go to the handle database with your handle URL, a specific handle URL. It's not a standard URL, it's a specific one, and that service translate this handle to the specific URL. For example, in my organization, I can move machines from service to service. I provide the handler provider with the changes in the URL, and they maintain the original handle, the fixed handle, and you can move the URLs. That's the point with persistent identifiers.
And in that case, who should be the handle organization?
There are many. By consensus, there are some of them, but there are organizations like the handler. Indeed, there are, for example, LifeWatch. LifeWatch is organizing to provide a service for persistent identifiers linked to the LifeBlock infrastructure. That's an example, but there are other infrastructure and other organizations that provide those persistent identifiers. What you need is a point of reference, a place where you ask, you provide that service, the handler, and that service gives you back the URL, so you can just look for this for the element. It's an indirection.
Yeah, and the key thing here is that the organization that provides you this persistent identifier is guaranteeing you that this will be available, quote unquote, forever.
Yeah.
Okay. They are explicitly saying that this will be available.
Because you're gonna sign service level agreements with the provider of the data. In those service level agreements, you say, okay, I can provide, I'm going to be the repository of the handlers, the persistent identifiers, etc. But when you move a specific service, just tell me the translation, and then you update the registries of that handler, updating the newer URLs and the new ending point for the services. It's not only data set, but also for services, for endpoint for services.
Okay, so shall we move on, or?
Yeah. Can we move on to the next part? Okay.
Okay, thank you.
I'm gonna share a screen.
There's no break, right? There's no break. We are going.
No.
Okay, once we are really aware of the capabilities, how to manage, how to provide, how to give everybody information. That's our real concern right now. But we all know that we live in the wild, wild west. It's not the web, it's the wild, wild west. So there are some security issues that you need to incorporate to the when you provide services or when you model the information. And so, indeed, when you define and you design the APIs that you need to use to access the information you are providing, that you are modeling, you need to take into account many of those elements. There are many of them, but I'm going to explain now some specific issues, very small specific issues that everybody needs to take into account when it's trying to model and define the data, the metadata, and the APIs associated. It's very a small glimpse, is because this is a very big field of research, and it's a moving target in the industry. So this is a small outline. First, about some recommendations for any of you trying to define the RESTful APIs. Some basic authentication types that all of you need to know because you are going to use them to access the information. In the end, some specific best practices to secure that APIs for those data sets and those services. So about the recommendation, there are 4 of them. One is how to protect the data, the use of secure services, how to prevent deny of services attacks, and how to prevent farming. About the data protection, okay. Today, all the APIs to access all the services, in the end, 90% are RESTful services, okay? And you need to take into account that RESTful services, the RESTful endpoints per se, they don't provide any security. You are using standard procedures associated to those for security in those data. But you need to take into account that a RESTful endpoint have a specific methods. Not it's only the get method that everybody knows. Get that information, get that information. You also have delete method, put method, post method, and you need to take into account that you need to define clearly the access rights for the use of those verbs, not only the get and get. Also, you need to take into account the delete, the put, and the post method. And those specific methods, in any way, can only be used without authentication. You always need to be authenticated before using those methods. You can say, okay, I don't care if people just get all the information. Okay, so get, I can provide a freely accessible get. But we can go later and probably you want to be really, really open, very fairness, and so you provide the get method in the open, and that is going to be a real problem later. Let's see later. About the security. The standard security process uses for all the REST services are the standard TLS that right now is available in all the web. Indeed, since 3 years ago, a big change in all the web have been developing, and that big change is that all the services, all the webs are now secure by default. Secure by default. Nobody provides a service or a website or a web service without a security layer. Nobody. And that is the standard that also all the web services are integrated with this kind of security. They do not use another way to secure the system. About the denial of service attack. Question is very easy. You need to prepare your system so when you are asked a verb, a get verb using REST API, you need to take into account to acknowledge those requests, maintaining a specific time, a timeline for those for acknowledge those requests. And if you detect lots of requests for a specific point, you need to identify them and block the access because you've been under a denial of service attack, because they can just ask you for a specific element in your data set from different point, but it's not a full access. They just say, okay, give me that information with the API, but it's not a complete request. It's a partial request, and you say, okay, that information is available, but you have made a mistake. It's the usual response you do to that request. That you need to identify those malformed requests because it's the base of a denial of service attack. And that implies that when you model the data, you need to be very careful not opening many final open elements in the hierarchy of your information, because those open points are the base for the attackers to explore your API and then attack your system. About the anti-farming, it's very similar, but in this case, question is that many system outside in the Wild West, they read all the information you are providing through your APIs, and they collect that information and redirect and offer that information for other parties, just copying all your information that you have been providing an organization. So you need to provide some authorization and authentication mechanisms to leverage how much information, how many requests are you going to allow for a third party. About the authentication mechanism. This is a moving target also. There have been in the last year many different of authentication mechanisms. But in the end, you can see that there are 5 specific authentication mechanisms, and those mechanisms have been evolved from the basic one to the Json Web Token, that is the more recent, and many organizations are pushing for using this kind of authentication mechanism. The basic one is really simple. In the HTTP protocol, you can put in the header or in the URL, you can put the password and the user ID. That's all. Indeed, you can just encode using base 64 standard. You can encode that user and that password and make them as a header like this one, authorization basic, and that header. And it's a way to access that information. Which is the problem? The problem is that if you are using HTTP without a secure layer, this basic mechanism is in the open. It means that everybody can just get that user, that password, and access the system. It's really simple to implement. It's really simple to use, but be careful with that because you need to assure that you are using a secure transport layer. Everybody knows about API keys. This mechanism is really simple and is used by a large group of organizations. It's very useful. I want to access to that API. I want to access to a specific resource. I ask for an API key. They provide me that API key, and I put that API key in the header. Perfect. It's really good way to access that information. Problems. First, you need a secure transport layer also available. Sorry. If you don't have a secure transport layer, in the end, people just can monitor the network and get your API keys. Also, it's very common that researchers wanting to be really open, they of course upload to public repositories the source code of the system, and they usually forget to clear the API keys. There are thousands of GitHub repositories with open API keys. Really, it's very easy to look for them. So be careful with this. Another way, it's more formal, is using SAML. It's a specific language based on XML. It's based on a single sign-on. It's a way just to agree with different service providers. So different service providers have agreements with a single sign-on organization or single sign-on provider, and all the services are accessible through a prior authentication with that single sign-on organization and provider. Problem with this one is complex to implement, but it's really open, and many organizations are providing this kind of authentication process. Similar is the OAuth 2, and OAuth 2 is a implementation really with a great popularity because Facebook, Google, Microsoft, Twitter, many organizations provides for the user. They provide that API, and you can use that API for authenticate the same users with your services. Be careful; it's not a free service, okay? But in the end, the OAuth 2 protocol provides you a specific access token, is an API key, and a refresh token. And each time you get a refresh token, the old token is erased, and so you can have a more secure environment than the prior one with only the standard API keys. It's a way just to add API keys. Finally, there is the Json Web Token. It's an extension on top of WAF 2. Oh, sorry. And this mechanism provides specific access tokens that are integrated as a JSON change for different scenarios. Let me just go through the example. First is an standard. You can go to that URL to read the standard, and it's really simple. It's really simple. It's based on getting a specific header, and that specific header is divided in 3 parts: the header, the payload, and the signature. The header is a way to define which algorithm and which codification you are using. This here is an example, and the base 64 encode in JSON. It's very simple. The payload is a group of claims about that authentication. You have an expiration, you have who provide that access, the subject, to who, a specific identification associated to the token. So it's a way to constrain the authentication in time or areas or a specific audience. And the last part is the the payload, where there are specific elements that are agreed between the client and the provider of the service, and these elements can be used as a way to provide a standard way to authorization mechanism, no authentication, authorization. It means once you have access to a specific area, a specific data set, a specific service, these private claims can be used to provide you the degree, the granularity of access to those elements. Read only, write only, whatever, for time, specific information you need to integrate or interchange. And of course, all of this is encoded in base 64. Finally, all these elements have a signature using a standard SHA-256 algorithms, and that all these elements with the signature is provide, let me see here. This is an example. You get, you go to this to access the server create all the secret and the elements that need to be provided. That JSON Web Token, once you have the secret, you prepare all the authorization header, and then you send that authorization header each time you need to access, you need to use that API each time in the header of the query. And the server evaluates the signature, evaluate all the permissions or that header accomplish and integrate. And once it matches with the permission you have been granted, provide the information you need. Finally, some specific best practices that really have a big impact on us as users of services and on us as providers of those services. First is limit the rate of queries. It's really important to limit that rate, and that is a implementation issue, but is a strategic one. Without a way to limit the rate of queries, any service is down in any time because of denial of service attack. That means that also the client, the user that use that API calls is impacted because you have a maximum number of queries that you can execute against a service. Second, the different authorization process. You need to make very, very, very clear and be very you need to protect and be very careful with the authorizations you assign to the different verbs in the APIs. Get, okay, more or less doesn't matter, but post, put, and delete are really, really dangerous. So you need to protect those methods. Also, you need to provide a wide list of methods. What it means, if I'm defining an entity with all the semantics and all the elements, I need a way to define, to restrict which verbs can be exerted on those entities, and explicitly list all those methods that are allowed. Also, there are some specific actions on some specific collection of information that is not a good idea to provide to everybody. So you need to protect those specific ones. And those specific ones normally are actions against big collection, getting all the collection or modifying all the collection of the information of the entities in that element in the API. You need a way just to restrict that. So you cannot sample just get all the information or erase all the information. If you block that access, then or indeed against the good practices of fair data and open data, you block that service, you block that point of access, better, because in other it's really beautiful to provide all the information, but not as a big export of terabytes of data. So you need to be very careful when you are defining those properties and those services. Of course, there are another different one like the cross-site forgery. In cross-site forgery, you are using an API key from one service, and you manage just to modify that API key to access other services. And there are elements that need to be taken into account for that. So the API keys, they are very useful, but you need to take into account all the problems around it. Finally, there are best practices around input validation. So if you are defining mechanisms, services around those specific data sets services you want to provide, you need to be you need to have a very granular way to reject validation that are not correct. It's better to reject a specific input than trying to sanitize or indeed validate in the final steps. So it's better if it's not easy, but in the upper layers of the implementation of the APIs, you need to implement a good mechanism to reject as soon as possible inputs that are not really validated. The same for URL validation, like SQL injection and the like. This, what it means? What it means is that in the end, we as services provider, we need to take into account all those elements. And as you can see, all those elements affects directly the openness, the fairness of the data, because outside is the world wild west. It's not the web, it's the west, really. And so we need to restrict some areas because otherwise you are really you're going to be dead in a matter of hours or days. Finally, there are some elements associated with the headers. You need to take into account the headers, integrated them, and please use the specific and the correct status codes for accessing the APIs and providing APIs for those services. And please, the number 401 is for no authentication. The number 403 is for no authorization. The names here, I don't know who defined those names, but the meaning is very clear. The first one, authentication. You are not authenticated, you cannot access this element, and you need to answer the query with this type of status code. If you have access but not the specific kind of verb, use this one. Using these guidelines, the services are easier to use and also easier to provide and are less exposed to the West. And that's all. Question?
Yeah, can I ask a question? Do you hear me?
Yeah.
Okay, I'm sorry, but I don't have any degree in computer science, so I didn't understand a lot of the things for sure. But I wanted to ask you from the global view, like me as a researcher, I would not work with APIs. It's more from the point of view of a web developer, or do I have to go into the details and read the whole night to understand your presentation? Because I didn't get
as a researcher, okay, it's very easy. As a researcher, probably you are going to use the machine actionable services to get information. So you, to prepare some kind of experiment, you are going to access information, retrieve that information, and then process that in your system, and you want to get that information and upload to a specific service, isn't it?
Yeah.
Yeah.
Without knowing that I use an API.
It's a way. Okay, if you are using virtual research environment, is your data. Okay, you get the information. Indeed, many times that information is not in your computer. It's in a specific virtual research environment in a specific service. Okay, but you need a way to connect that virtual research environment with an external service or an external repository of data, and then send the result to that repository of data, isn't it? Yeah. So you are going to use those APIs.
Okay. Yeah.
Okay. Probably the virtual research environment provider prepares you some specific user interfaces to make it easy. Perfect. But you need to be aware of that what is behind the scene. Because, as I mentioned before, all of us are pushing for open data and fairness. Perfect. In a fully ideal world, you can get all the information you want, you can analyze all the information you need, everything, okay? But in the real world, that's not true. You cannot get all the information without authentication. Sorry. Why? Because otherwise, the services are down due to denial of service attacks, for example. So you need to authenticate. You say, okay, I need to authenticate. Perfect. But also, you are not going to be provided with the access to all the elements at once. You can say, okay, I need all those elements and then analyze them. It's a very big load. So probably the service says, no, you need to ask me from just small subsets of that information. And you need to know that for asking for that information, for the resources, you need to use a range of data. And all of that, the reasons are security reasons that impacts in the way that you need to use or you are going to use the services. So having a small idea, a high-level concept about those issues, then you understand, okay, I understand why that services is working in this way. That's my objective. Sorry.
Hello, I am asking again. My question is for those researchers that are going to publish with the open access of data, right? And what do they need to know about specifically, basically what she asked before? What is the main important thing that they need to know in order to publish the data with security?
Okay. It depends of the services. Okay. Let me put an example. You have a provider of repositories of data, of open data. Okay. First, you need to know the license you are going to attach to that data. Second, you need to know if there is any period of embargo associated. It's very important to know that. And they are both accepted by the fairness, the definition of fairness. Okay? Third, for a secure point of view, if that provide you a specific service, a secure service for the connection, HTTPS, with authentication, etc., perfect. But that specific user interface could be different. Perhaps it's some kind of web services that you need to combine using Python or command line or Cure, something like that, just to publish your data. Okay. Also, from a security point of view, the correct authentication of the person who is uploading that information is a critical element. So it's so using it's not common, but for example, you are a group of researchers, okay? A group of researchers doing some research in a specific area, okay? You need to take into account that who is going to upload that information. And probably you will need to have a specific way to define all that information is provided for all of us, but we are using this common authentication, this common specific user. You need to have that kind of element. You need to take into account that that kind of concerns. Okay, and also the problem about the data you are providing is, okay, I'm providing data. I'm providing data using this kind of metadata that is standard. All the standard metadata and systems that provide that standard metadata have no problem because all those issues are automatically detected, okay? The system that provides that information is okay. But if you are going to define a specific semantics for some way to structure all the information, and you are studying this kind of semantics, and you define that semantics, you need to annotate that semantic with the restriction of the access to make that more restricted, because otherwise the system doesn't know how to provide the user of that information the request. Say, okay, give me all the data. If you don't have no restriction about the granularity or anything at all, the system just provides you all the information, and you all perhaps you only need a specific subset of all the information you have provided. And so you are defining the metadata. You're defining the specific vocabulary or ontology of the data you have provided to the system, isn't it? No, it's not a specific file. There's a group of files, and you define the ontology for that information. You need to define a specific restriction on how to provide a specific element or not to provide a specific element, because all the semantics providers, in the end, there are RESTful services that just read the information from the metadata and the ontology and convert that information in a specific API calls in the web service. So you need to you need a way to define the restriction to those access, because you need only one element, another element, but not all the elements as an example. So you need to take into account that you need to define some way to restrict the access in the annotation, in the structure of the ontology, associated to the ontology, using other ontology, whatever, but you need that. Because otherwise, the service just can say, okay, I'm going to provide just only 5 elements each time. And perhaps the structure of your data need to provide 12 elements because it's the complete set. You need to provide those hints to the service.
Okay, and how to define the API elements? This is a work that has to be done between the researcher and the IT person behind, like a person like you, right?
Yeah, there are, from the point of view of the implementation, you need to agree in a specific of the use of some kind of semantics, a specific vocabulary or ontology to define the granularity of the access. It's not only the structure of the information, it's also the granularity to access that information and the volumes. And from that element, those hints, the implementation of the service can use those hints to serve the information in a proper way. Problem. There is no standard right now. There is no standard right now to do this. There is a lot of research for that. That's a real problem. Security issues in the research community is a very recent issue, a very, very recent issue. We are working on that, for example, from lifecycle, very deeply, because it's a real concern for us. But it's not. It wasn't a real concern 2, 3, 4 years ago. Nobody was working on all the implication of the securitization, service and different service, web service and data set. Nobody. But you need to take into account now this, because right now we are in the wild, wild west, really.
Many thanks. It's very clear.
Hi, I have a question about the REST and RESTful services. I'm not really familiar with what that means, but so I guess you can talk a lot about it, but I guess it would be helpful just to spend a few words on concepts concerning these lessons. That would be helpful. Allow us to understand,
I don't know if Jose Maria, you have a specific elements in to get it using the REST interface.
Sorry, say again.
Do you have in the hands down example? You have a REST example?
No, unfortunately, no.
Okay. So, okay. I'm gonna look for a specific one, just to a specific example. But
just to give us the very general picture.
Yeah, the general picture is very easy, very easy.
Yeah.
Initially, in the very beginning of the semantic web and the data and the like, okay, in the very beginning, the way to get information from a system was using SOAP, okay? Just using XML and SOAP. So you have a URL, a unique URL. You send that URL using the SOAP protocol a query, and that unique URL replies you with a big XML with all the data, the information, and the like. It was in the original SOAP, the protocol for service-oriented, okay, in the web. There were many problems with that, many problems, because XML very big, complex. In the end, it was not a good idea. So years later, people were just working on a streamlined, very lightweight mechanism for access that information. And the mechanism is really simple. You have the URL, and behind the URL, the initial URL, you have a path with several levels, and in that path is the way you go. It's a tree through your data. That's the simple case. You are going from one element to other element in your data through that path. And once you have reached the end the final element in that path, okay, in that tree, you have 4 verbs. Get, give me that information, give me that element, and so you get in a JSON or XML or whatever, you get that information. Perfect. Put, you update with data you provide to that in that element, you update the information in the server. Post, you create in that path a new element, okay, in the graph, a new element, and delete, you delete that element. Okay, that's the 4 verbs, basic verbs. That is REST. It's a very, very simple way, very simple way to access the information. So the servers implement a way to navigate, to go through the graph of the information and get that information from different data lake, databases, whatever, and provide you that information. But the servers need to implement a graph of all the information. That graph, where you get that graph? From the semantic web, the semantic of the data. So the services, those servers read the description of the metadata, of the ontology and the like, and then they know what is the information you want to get. And get that information from the data lakes, the server, the services, and whatever you have under the hood. Okay, that is REST. Right now, 90% of all the services in internet are REST services. But there is some funny elements here, because right now many people are starting to get okay, defining REST is very cumbersome. You need to work a lot for defining those REST services. So in the end, people are getting some approximation using GraphQL and something like that, okay? It's the next step. In 20 years, less than 20 years, we started with SOAP, then REST, now GraphQL and some elements associated, okay? And it's a moving target. What is more or less fixed is how to define the ontologies, the way you define the elements, RDF, all, etc. But the implementation details have changed. Probably in the end, you are going to have right now in 3-4 years a mix of REST services or RESTful services, okay, strict or not strict, okay, and GraphQL and something additional, because systems are really complex to develop. You need and you need to be very careful with all the information that you implement.
Okay, I see. Thank you for the explanation. If we have a little more time, I have one more question about the conclusion from your previous explanation on data security. I mean, I was wondering if the recent concern about data security arised from the use of open data, so data that follows the FAIR principles, or if it has already been there and we are now addressing all of these rising problems.
Okay, the real question here is that security has been neglected by researchers and by fairness proponents from the very beginning. Neglected, completely neglected. Sorry, but that's true. Sorry, I'm not politically correct. Have been neglected completely. And now they say, oh, we must have thought that previously. Oh, we have a problem. Houston, we have a problem. A big problem right now. So, okay, the expert in security, they're working on ways just to laminate those problems, okay? Using standards, using best practices. For example, one way is the way I have explained to you, just being very careful with the way to access the information, okay? Perfect. And the way to develop those elements. There's another way. Another way is to create a firewall, an application firewall, before your services. So you have your service, your server, the services that are provided, and before that, you implement an application firewall. We are implementing application firewall in LifeWatch as an example. Because you cannot, there are a lot of legacy services that didn't take into account security from the very beginning. The new services we are working on, many of them have integrated those security concerns and best practices. So in the end, you need to combine the two approaches, creating and being aware of security issues and security concerns in the definition, in the semantic definition and the implementation, perfect, but also provide a firewall. How do you create that firewall? You need semantics to define the properties you want to restrict, okay? You need to use semantic for that also.
I see. Then I mean, then thanks to the semantics you define, you basically help the firewall doing its job, right?
Yeah, but you need to combine the two approaches. You need to combine both. Okay?
Yeah.
If you can implement some security concerns in the implementation of the semantics in your datasets, okay, perfect. But also, you need to define using another, it depends on the ontologies and vocabulary you are using, okay? You need to define using a specific vocabulary for security, the definition of the rules of the firewall, and any access goes through that firewall, and the firewall analyze the query and say, that query is incorrect. You cannot do that. Okay, you could do that, but it's going to be a real nightmare for all of us. So block the access.
Yeah, I think I understand more. Thank you for the explanation.
You're welcome.
Okay. Anything else?
Another very short question. So I understood the idea of risking that somebody might harm your data, but about what other risk concerns would research data face?
Sorry, would you mind repeat the question?
Yeah, so I understood the idea of farming, but what other risk concerns could we be facing when we have research data? What else could we misused?
There are many. For example, tampering. You can just in some areas. For example, I have a service with all the research data, okay, and you need to access that URL to access that data, okay. You can do some kind of tampering or some kind of DNS redirection, and some queries, instead of provide that research data, you are providing a fake research data. That is, there have been some attempts from climate change deniers and blocking access and changing the information. I think, from a personal point of view, research information is fundamental for the society. You need to secure that information. You need to assure that that information is the information the researcher provides to the server and the system and the like. Okay, you need to assure that, and so you need to use all the capabilities and all the years of study of secure system just to guarantee that. It's a part of the provenance, for example. It's a part of the provenance, but it's not only the provenance in the service, it's also the provenance accessing the service. So you need to extend the first principles. That's a question. That's my concern with the FAIR principle. It's okay, perfect, no problem. But they didn't take into account security from the very beginning. That's the point. That's my point.
Okay. Can I ask you, do you have a good example of temperate data, climate data that you can refer to? No, something that
there were attempts, but those attempts were very they were detected. basically it was a change in the DNS. In a DNS, in an area, the DNS to accessing the information was changed. So the servers were not, you had a clone of the server, but without the information. So the reports were not available. That happened during the first months of the Trump administration in the USA. They got the access to many areas. And that's the reason a lot of information were collected and put in the archive.org.
Thanks.
Okay. Maybe since we only have 10 minutes and we didn't have a break, I mean, if there is no more questions on this last part, I would just like to give you a little assignment to work on it, on some of the concepts that we have said today. And I will just present you the ideas and the tool. And since we have a slot on Friday, right, Lucia, I think, maybe we can also get together there and you try to work on this little exercise, simple exercise, just for especially for you that you are not that knowledgeable with semantics and vocabularies and so on. So you try to work on it a little bit and see what can you get. Okay. So let me see if I solve my share screen issues. You can see it, right?
Yes.
Great. Okay. So the idea is that you basically get together and work in developing, on trying to develop an ontology or a vocabulary on some specific use case that you may bring. Okay, so the idea is that we use a tool, an online tool, which is called Web Prodigy, to collaboratively develop this vocabulary. And for that, I suggest you to try to form groups directly in the WonderMe room. I think that this room is always available, right?
Yes.
So you can go there just by using the password, okay? And it will be good if you try to, maybe in the next 5 minutes, you just enter there the group and try to talk with each other to form groups. The idea is that maybe 4 to 6 members will be nice, and this is very nice with this tool that you can just move around groups and try to find out a place. So we can make it quite dynamic there. The idea is that you try to mix and match different backgrounds on your knowledge about semantics and on your different positions that you have in your work. And then some of you may have a good use case of some research data, okay? And the idea is that you try to model this data using vocabularies, okay? So you will have to create classes to represent the entities that goes into that use case, properties to refer to attributes of those entities and how those entities are related, maybe even with other different classes, and then try to create some instances or individuals that correspond to those concepts that you created, so that you have just a quick sample of the process of annotating, of creating some vocabulary and expressing or describing your very real data with this vocabulary. Option 8 would be good if you try to find some other vocabularies or metadata ontologies, some of them that I refer to during my presentation. You could have a look and try to add these properties to the instances that you create there, okay? And let me just show you, in case you didn't know the tool. So if you go to the link, maybe I can also put the link on the chat. Okay, so if you go there, you have to sign in, and then you have to create your user if you haven't done it before. And then from here, basically the idea is that you create a new project here. You can start with an empty project, or you can import some initial ontology. Maybe if you want to use a specific vocabulary, that will be also nice to do. For instance, you could actually have a look, if you are knowledgeable with ENVRI reference model, you could take directly the ENVRI reference model and import that model there, and maybe describe some data sets using the model, or try to use it. But as you will see, once you open this project, I mean, this is a project that is already filled with data. You see here basically a class tab where you can create the different classes and subclasses. It's pretty simple. Just you go. Okay, why I cannot create a class now? Okay. Let me just create a new project. Okay, now So you just click here on this button. You can create the classes. I don't know, dataset, whatever. Okay. There you can have some annotation on this class, and you can basically from the properties tab, you can create different properties to those classes. There are object properties and data properties, and also annotation properties. In general, data properties is used for having properties with literal values. And if we have some properties which relate different entities, then you need to create an object property. Again, it's just create the name, and then on the property that you create, you can specify the class for the domain and the class for the range. You can put there several classes. And in the individuals tab, you just create different individuals. And let me see if now it works. Okay. So in this example of this pizza ontology, this is a well-known example in ontology development, where you basically have here a classification of different pizzas. And basically a pizza is defined as something that has a base, that has a pizza base and has some pizza toppings there. Okay, and there are many different, as you can see, types of toppings, fish toppings, cheese toppings, and so on and so forth. And then the properties, you see that there is a has ingredient property, which has as a property has base and another has topping, okay, which the domain and ranges already set there, as you can see, okay. So that basically we can create a data set about pizzas. And then here in individuals, I can, for instance, create my tasty pizza. We create an individual, it will be an instance, okay. And then here you say that this is a pizza, okay. So you create a pizza. You see that the interface is very simple, and and then you can create here in relationships the different properties. So this pizza has the topping, and I put here, for instance, ghost cheese topping, okay, and also some meat, spicy, hot spicy beef topping, for instance, okay. So you basically create like this in a very simple manner the different elements of your ontology on the one hand, and also the actual instances of the data, okay. So that's basically the idea, that you basically try to work with this environment together and come up with some example that we can maybe discuss on Friday during the free work session that is scheduled. Okay, I will try to be. I won't be available for the whole slot, but I will try to be there for.
Jose is not here anymore. Maybe he has some network problem.
Yeah, I think so. I think so. But I think that okay.
Okay.
Yeah. It's coming now.
I hit the wrong button. Sorry. So that's it. So, sorry, I was just saying that that's the idea. Please go to Wonder and try to hang out there and form some groups and maybe call it a day. And I think that tomorrow we also have a session, right?
Yes.
Okay.
Sorry, Julio here. I have a question for Jose. How do we work together on making the ontology if each of us has one account on the platform?
Sorry, I forgot to mention that. Thanks for the question. So
Okay,
in Web Protege, I'm sharing the screen again.
okay.
So in Web Protege, if you go here at the right top, you have a share button, okay? And you can share with specific people with the usernames there, or even easier, you can just click on link sharing enabled. You give edit rights, and then you can just copy the URL to each other, and you can access the same project, so that you can collaboratively create their different parts of the ontology, for instance.
Okay, so let's say one per group have to create the project and then share the link with others.
Exactly.
Okay.
Yes.
Okay, thank you.
Thank to you, because I completely forgot about saying that.
You're welcome.
Okay, now I hit the correct button. Okay, so I think that's all for this session. Thank you very much to all of you for being with us for these 3 hours, and I hope that you enjoyed and you got some good getaway messages and good knowledge about what we talked. And see you in the next sessions.
Thank you, Sam. You will find all materials on the ENVRI training platform. You already have the link. I will put it as soon as possible, also the second part. Okay, thank you. Have a nice day. Bye-bye.
Thank you all. Bye.